Okay, so I am going to go ahead and introduce Dr. Benning. He is a Monfort Professor of Atmospheric Science here at CSU, and he leads a large research group focusing on understanding the metabolism of the Earth's biosphere. So hopefully he'll tell us a little bit more about that, maybe not today. He's also well known in the climate literature, having published numerous articles on the topic of climate change. He's the former editor of the Journal of Climate, and he particularly enjoys engaging audiences around the topic of climate change. So hopefully we'll get to learn a lot more today. So thank you very much.
Thank you. Thank you for having me. So I would like to talk to you about climate change today, and it's billed as a lecture, but I hope that it's actually fairly engaging and entertaining, and not entirely sonorous lecture-like. There are three S's that I want to cover for sure. Climate change is simple. That sounds a little odd because sometimes what you hear from people is, oh, it's terribly complicated. You have to read, thick stacks of reports and consult with experts and so forth. I aim to show you that it is not like that it's actually quite a simple idea and that it's completely consistent with your everyday experience. I aim to show you that it's serious, that in fact the consequences of climate change will eventually become so serious that everyone will understand that it's a big problem and that the problem will in fact be solved. That's my third S. It is solvable. It is not something that's, bury your head in the sand, oh my gosh, it's the end of the world, we're doomed. I don't believe that we're doomed. I suppose that part is not so much a scientific opinion as just my opinion as an informed reader and citizen. But I do a lot of these presentations about climate change, and I never, ever do just one or two of these S's. I try to, even if it's a 30-second conversation in a supermarket, or it's not like we have a lot of 30-second elevator rides in Fort Collins, but there are such things. Elevator speech, all three S's, absolutely crucial. You can't just pick the doom and gloom stuff and talk about that. So there are some common myths about this, and I want people to be skeptical about these myths. The first one I've already kind of alluded to, that climate is complicated, that you have to trust experts, that you have to read a whole bunch of technical manuscripts and sort through them. Baloney. You are plenty expert enough to understand this problem yourselves. Another very common myth is that the concern about global warming arises because it's been getting warm. Now, it's true. It has been getting warm, but that's not what motivated scientists to be concerned about climate change. This is actually a problem that was predicted 150 years ago, long before it started getting warmer. So this is not the case. This is an important thing, because a lot of times the way you hear this talked about is that if somebody could just find some other cause for the recent warming, I mean, this is why we keep hearing about the sun and volcanoes and natural cycles and things like that, then we'd be off the hook. Well, baloney. Even if all the previous warming was caused by something else, that doesn't mean we're not going to have a whole lot of warming in the future if we put a whole lot of CO2 in the air. Another thing that is wrong but is out there is that this whole thing is a theory based on some kind of complicated computer models. I will not use any computer models in the talk. I'm going to appeal to your intuition, to your experience, to your everyday experience with the world, and ask you to be the judge yourself. You don't need to be a technical expert to do this. Probably the most pernicious myth of all is that if we stop burning coal, we'll freeze in the dark. When this issue is framed as we're either going to keep doing what we're doing or go back to the Stone Age, no wonder people will react badly to that. Nobody, well, not many people want to go back to the Stone Age. I don't know. But one of the things we got to put away right at the beginning is the difference between weather and climate. I think most of you have been in this region long enough to know how to finish this sentence. If you don't like the weather, Hey, very good, very good. It's like I knew what you were going to say. Isn't that something? So wait 5 minutes. The weather changes a lot, right? It was really cold this morning when I got up and took my kid to school. And it's really nice out right now. That's the weather, right? The weather changes literally hour to hour, certainly day to day, week to week. Sometimes, especially this time of year, I don't know if I have time for these little digressions, but back when people used to read the newspaper around here, on the back page of the newspaper, they always had the record high and record low for that date. And all winter long in Fort Collins, from before Christmas until roughly the end of February, the difference between the record high and record low temperature in Fort Collins is more than 100 degrees Fahrenheit. Every day, all winter long, you can get anything as different as 100 degrees Fahrenheit difference in the temperature for that day in the 120 years of records that we have. The weather is incredibly changeable. Not so with the climate, okay? If you don't like the climate, move. You're out of luck because the climate isn't going to change from Monday to Thursday. The climate isn't going to change from one week to the next. The climate is the envelope within which the weather bounces around. The climate is the average weather. Look at it like this. Climate is place. Okay? Climate is place. We have a climate here which defines our place. And you've been other places and they have other climates. Been to Arizona. It's different there, right? It looks different. The cities are organized differently. The agriculture is different. The whole landscape looks different because the climate is different. And it's not like it's only different today and it's going to be different than that tomorrow. The climate is a long-term thing. That's what makes that place different from here. Think about Alaska versus Hawaii versus Australia. These places are very different places. And they're not just different temporarily for a day or a week or a year, they're permanently different. Of course, you learned this I'm a little vague on this. Did you learn this in the 3rd grade, in the 5th grade, something like that? Latitude, right? Latitude defines the climate. We have a different climate than Alaska. We have a different climate than Brazil because we're at different latitudes. The latitude determines how high the sun is in the sky and what the day length is and so forth and the seasons of the year. Around here we know that climate also depends on altitude, right? We have a different climate here in Fort Collins than they have in Breckenridge. The altitude in this part of the world is a huge determinant of our climate, and it's not just on Tuesdays, right? It's like that in a sort of semi-permanent way. There's a little bit of a dependence on what's upwind. So if we pick two places that are the same latitude and the same altitude, let's say Seattle and Montreal, I guess for you, I'm backwards, right? Seattle and Montreal, they're both right about the same latitude, they're both right at sea level, but if you go this time of year to Seattle, the grass is green and the flowers are coming up. And if you go to Montreal this time of year, it's white, right? It's completely frozen this time of year. And the reason is because upwind of Seattle is the Pacific Ocean and upwind of Montreal is all of Canada, right? So what blows in is much colder. So this is really common sense, and you really did learn this in the 3rd grade. You know, because latitude, altitude, and what's upwind don't change a lot, climate doesn't change a lot. It's a very slow, progressive thing that doesn't change, from day to day, from week to week. It changes very slowly, and believe it or not, it's very predictable. You've all heard the story, if they can't predict the weather next Tuesday, how the heck can they predict the climate 50 years from now? Kind of makes sense. But it's wrong. I can predict the climate in the future. Watch me. It's going to be warmer in Fort Collins in July than it will this month. And I can do that year after year. It's going to be warmer this year in Miami than it is this year in Minneapolis. And I'm right every time. It's not like it's got some error bar on it. I'm completely right about these things because climate is predictable. Climate is really all about heat in and heat out. Did you ever wonder why day is warmer than night? No, you kind of know this, right? Do you ever wonder why summer is warmer than winter? Why Miami is warmer than Minneapolis? These are not difficult predictions to make. These are very sensible, and you know them without a large error bar around them. It's all about heat in and heat out. When more heat comes in than goes out, things warm up. When more heat goes out than comes in, things cool off. Now, weather, so if we have colder weather, 1 week than the week before, that's all about heat coming in and out the sides. The warm air gets pushed out, the cold air gets pushed in, the weather is different. But when we talk about global climate, we're talking about the world is round. There aren't any sides. You can't push stuff around sideways to make the climate different. What the heat going in and out of the earth as a whole can't come through the sides. The only way heat can come in and out the earth is through the top. Okay, this is kind of weird, but the earth is round, and when we say the top, we mean the outside, right? The outer space, outside the earth. Heat comes into the earth, you know where it comes from the sun. Heat has to get back out. If the heat only came in from the sun, the earth would get hotter and hotter and hotter and hotter until something terrible happened. The earth has been receiving that sunlight all this time, and yet it doesn't get, infinitely hot. So there's got to be the same amount of heat going out as coming in. How does it do that? I don't know if you learned this in the 3rd grade or the 5th grade or the 7th grade or whatever, but there's 3 ways you can move heat around. There's conduction, convection, and radiation. Did you remember this vaguely from grade school? So conduction is where you grab a metal rod and you stick it in a Bunsen burner, and after a while you have to let go, right? The heat is conducted along the metal rod into your hands, and ow, it gets hot. That can't happen out into space because there's nothing to conduct it to. It's a vacuum out there. It's a void. Convection is where hot stuff moves from one place to another. So you put a pot of water on the stove, and the convection, currents of hot water move around in the pot. Again, you can't convect heat out away from the earth because it's in a vacuum. There's nothing to convect out to. You suppose you could get rid of the air and it would carry some heat away with it, but the air is stuck to the earth with gravity and it can't go there. So the only way to get rid of the heat is radiation. Radiation, it has this kind of negative connotation. You think of radiation, you think of like nuclear weapons or something. But radiation includes light. Radiation includes heat that you can't see, that is thermal radiation. Radiation is the way we detect the world. It's certain wavelengths that trigger the little retina in the back of our eye. It's how we can see where we're going. But all of you have the experience of heat radiation which is invisible. If you've ever used an electric stove, you turn on the burner, and before you can see anything coming out of that burner, you can feel the heat coming off of that burner. That's heat radiation. That's energy being transferred out of that burner into your hands, and you can feel it at a distance. So heat radiation is the whole story, with energy getting into the earth from the sun, that's radiation, and energy getting out of the earth through heat radiation going out to space. Everything radiates. Table, floor, ceiling, people, walls, everything is radiating heat depending on its temperature. The hotter something is, the more it radiates out. And that heat radiation going out has to pass through the air. Okay, there's this one little sciencey thing I got to talk about that's not sort of 5th grade science. This part is a little bit harder to follow, but bear with me, it's not that bad. 99% of the molecules of air in the atmosphere are just 2 gases, oxygen and nitrogen. Okay, 99%. Oxygen is that one on the top, nitrogen is the one on the bottom. 80% nitrogen, 19% oxygen, give or take. Together they constitute 99% of the molecules. The radiation that's coming up is electromagnetic waves. Okay, that's big, lots of syllables in those words. But basically it's energy going out of the earth that is oscillations between electrical and magnetic fields. And as they're going out through the earth, maybe you didn't learn this in grade school, but magnetic fields can grab onto the shared electrons of these molecules and start them swinging back and forth. Basically, any kind of magnet that goes past electrons that are shared between these molecules will start the molecules vibrating. And when those molecules vibrate, some of the energy that was going out to space is now trapped in the vibration of the molecule. So basically, electromagnetic energy has been turned into kinetic energy of the vibrating molecule. Think of it like it's singing. I know this isn't really true. I'm making this part up, but think of it like the molecule receives this energy and it goes woo, and that energy of vibration is now not on its way out to space. Now, conversely, a molecule can release radiation energy by de-exciting or unvibrating. So it goes woo, whoa, 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 back to its ground state, and a photon of energy will go up, down, sideways, whatever, and go away. But because 99% of the molecules in the atmosphere are made this way, of just two atoms of the same element, that's the only vibration it can do. It's the same no matter which way you turn it. There's no other motion that this molecule can do. Less than 1% of the molecules in the Earth's atmosphere contains 3 atoms instead of 2. The 2 most abundant gases in the Earth's atmosphere that contain 3 atoms are these 2 atoms, or molecules, carbon dioxide and water vapor, CO2 and H2O. These are what we call greenhouse gases, and let me tell you why. Because just like O2 and N2, the CO2 molecule, we only got the 2 hands, so we'll make this one carbon, okay, oxygen, oxygen. Just like O2 and N2, CO2 can absorb a photon and go woo, 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 whoa, 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 back to its ground state. But there's more. Because unlike O2 and N2, it can go wee, boom, wee, boom, wee, boom, wee, boom, 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 boom. So all of these different ways to wiggle that molecule will absorb a different wavelength of energy, a different color, if you will, a different frequency of photon. And that's what makes this molecule a greenhouse gas. Water vapor is even better because it's bent, okay? This is H2O, and because of that bend, you know, you can imagine it going wing, wing, this way, like see this way. It can even do handsprings, and I shouldn't try that because I'll probably get hurt. But these molecules are excellent at absorbing thermal photons, thermal energy that's being emitted to space, storing it temporarily in the vibration and oscillation of that molecule, and then re-releasing it back out. If it goes up, great, it cools the Earth. If it goes down, great, it warms the surface of the Earth. And in fact, we can measure the heat coming off of these molecules. And to a very large degree, this is what keeps the Earth habitable. If it weren't for the downward heat being emitted by these molecules of gas in our atmosphere, we'd freeze to death. If you go outside at night, this time of year, it's cold. But it's not as cold as if it would be if it weren't for this heat streaming down from the warm sky. Believe it or not, measurements have shown, and it's a trivial measurement to make, I do it with my classes, if you take this ATS 150, we'll do it. Go outside, you can measure the heat coming down from the sky. You can measure the heat from the sun too, right? Obviously you can feel the heat coming down from the sun on your forehead. But if you measure the heat coming down from the sky, it's not just during the daytime, it's nighttime too. It's all the way to the poles, and there's twice as much of it as there is sunlight. Literally twice as much heat reaches the surface of the Earth having been emitted by the warm sky as the heat that comes straight from the sun, because the sun's only in one place in the sky, whereas the rest of the sky is everywhere. So we absolutely depend on this greenhouse effect to keep us warm, to keep the oceans from freezing solid. Okay, I got a little movie to play for you here. So before it plays, I'm going to tell you what happens in the movie. It's very short. It's kind of fun. It was made by the Little Shop of Physics here in CSU. And what the movie does is show you that you can actually see the heat emitted by CO2 gas. Okay? It's all around us. It's emitting heat all the time, just like we're emitting heat. But O2 and N2, because they're simple 2 molecules on a bond, can't emit heat very efficiently, and CO2 can. And the way we're going to show this is we're going to show you a blow dryer blowing at somebody's face, and you can't see the hot air. You can see the face emit heat in the thermal part of the IR spectrum, but you can't see the hot air. Then we're going to take the same thermal video camera outside, and we're going to video car exhaust. And lo and behold, you can actually see the car exhaust glowing in the infrared, where you can't see hot air glowing that comes out of a blow dryer. And the reason is because of the greenhouse effect of the molecules in that car exhaust. Oops, no, that's not working. Hold on. So bear with me. You could turn off the lights in the back. So you can see her face glowing, but not the air. That's CO2. You can literally see it glowing. This stuff is CO2. It glows in the dark. All right. So you've seen this slide before, the greenhouse effect, summarizing the radiation from the sun warms the Earth. Some of it bounces back off to space. The Earth has to get rid of all that radiation by thermal emission. Some of that thermal radiation going out makes it all the way out. Some of it gets absorbed by these greenhouse molecules in the atmosphere, re-emitted back up, back down. The part that emits back down keeps us warm, keeps us toasty. It's a measurement. I'm not making this up. You saw it on the thermal cam. If you take my class, we'll show you a little more quantitatively. So think of this. This is common sense. If you double the number of CO2 molecules, these bouncy things up in the sky, it will add this much heat to every square meter of the Earth's surface. Now, some of you are too young to remember what these things are. These are incandescent light bulbs. They are 4-watt light bulbs. When my kids were little, we used them as night lights so they could find the bathroom in the middle of the night. When I was a boy, we used them for Christmas tree lights. But 4-watt light bulb. And if you double the number of these heat-emitting molecules in the sky, you put 4 extra watts on every square meter. So this is about a square meter. Imagine a light bulb right there, and another one here, and here, and here, and here, and here. The entire Earth covered with these suckers, 24 hours a day, 7 days a week, pretty much forever. That's going to warm up the surface of the Earth. It may not make the surface a lot warmer, but it's going to make it warmer. And that's really the story. That's how CO2 warms the surface. And believe it or not, this was known before light bulbs were invented. This measurement of how much CO2 emits, how much heat CO2 gas emits, was first made by this guy, John Tyndall, during the Lincoln administration, that is during the US Civil War in 1863. The samples of CO2 gas were put in a machine that could measure the heat being emitted by them. And the 4 watts per square meter calculation was first done in 1898, but the heat radiation was first measured in 1863. So when I say that we're not we didn't just start worrying about this when it got warmer. Back in 1863, it was demonstrated that burning coal produced CO2, that CO2 produced heat, that heat warms things up. So this is my favorite common myth, number one. People are worried about climate change because it's been getting warmer. Well, it has been getting warmer. And most people will start a climate change talk with this graph that shows that way back in 1860, the temperature was doing a certain thing, and then towards the end of the record, it started going up. Well, that's all true, but that's not why we think that greenhouse gases will warm up the surface. We think that extra CO2 will warm the surface because we think that when you put heat into things, they change their temperature. Okay? When you put a pot of water on the stove, you put heat into it, it changes its temperature, right? You have all experienced this. Now, the idea that changes in heat are proportional to changes in temperature is formally called the first law of thermodynamics. But if you ask me, you have to be some sort of egotistical Victorian Brit to call something that simple the first law of thermodynamics. For goodness sakes, cavemen knew this. You put a slab of mammoth on the campfire and it gets hot. They probably didn't call it the first law of thermodynamics. They probably called it hot. But this is the basis for our understanding that extra CO2 will warm the surface of the Earth because we know the stuff emits heat. And heat warms things up. So when people tell you, no, it won't, you better ask them, are you sure? How in the world can you put heat into things without changing its temperature? Maybe you can, but I want to hear the explanation. So 4 watts isn't a lot. Let's face it, 4-watt light bulb isn't a lot of heat. Even on every square meter, there'd be a heck of a lot of 4-watt light bulbs in this room, right? If we put one on every square meter. How much warmer are we talking about? Maybe you've heard there's a number out there. If you read about this, the number is 3. Okay, what am I talking about? Doubling CO2 is expected to warm the Earth by 3 degrees globally. And this is a number that's been around for a long time. Since more than 100 years, people have been saying 3 degrees of warming per doubling of CO2. But these are maps that intend to calculate how much warming you get in different parts of the world. And the first thing you ought to notice about the maps is that they're not all the same color. Okay? So it's not true that even if you had 3 degrees of warming, it's not 3 degrees of warming everywhere. That's the global average. But some places get more than 3, some places get less than 3. The first thing that you might notice about this is that the land gets a lot more warming than the oceans. And that makes a ton of sense too, because the oceans are very deep. Did you know? The oceans on the average are 13,000 feet deep. That's very deep. And it takes a lot of watts to warm 13,000 feet of water. So places that don't have 13,000 feet of water to warm up a lot quicker than the places that do. So the land warms up more than the oceans. The next thing you might notice is that the southern hemisphere warms a lot less than the northern hemisphere. And again, this makes a ton of sense because the southern hemisphere is mostly ocean and the northern hemisphere is mostly land. The third thing I want you to notice is that the Arctic, the snowy places, the snowy parts of the world warm a heck of a lot more than the places that don't have snow. And again, this makes a ton of sense because snow is bright white, reflects sunlight to space. You get rid of the snow, it's dark, it soaks up more sun. It's like the difference between an asphalt parking lot and a skating rink. If you put the same amount of heat on both of them, the asphalt's going to warm up a lot more. So if you happen to live in a place that's on land in the northern hemisphere where it snows, you don't get 3 degrees, you get extra, so that the average can be 3 degrees. And that is where we live. If you look at the middle of North America, where we live, in that low emissions world, you get about 3 degrees of warming. In this high emissions world, you get about 6 degrees of warming. Oh, but wait, those are Celsius degrees, right? Because this is one of those sciencey things that everybody uses Celsius. Here in the United States, we use Fahrenheit. I mean, I'm a climate scientist, but when I check the weather in the morning, I'm thinking Fahrenheit. So you got to multiply by 1.8. You probably learned that in grade school too. And so 3 to 6 degrees of warming is actually 5 to 10 degrees of warming in the units that we're familiar with. So 10 degrees. Even that doesn't sound too terribly bad, does it? let's face it. You know, this morning when I went out to take my kid to school, it was like 15 degrees out, and if it had been 25, I probably would have been quite pleased that it was 25 instead of 15. But we're not talking about just this morning, right? That's the problem, is that we're talking about on the average. And on the average, climate determines what places are like. Remember, climate is place. Climate change is place change. What does a 10-degree change in the average temperature look like? All you have to do is look at a map of the United States. This is a map of average high temperatures in Fahrenheit, and each color is 5 degrees. So pick a dot that's near where you live and move it 2 colors on the map. That's 10 degrees of warming. You know, we're moving to Texas, and Grand Junction's moving to southern Arizona, and someplace in Illinois where I was doing this talk is moving to Mississippi. Washington, D.C. moves to something like Tallahassee. So 10 degrees of warming doesn't sound like much, but it sure as heck is a lot when you look at a map, right? 10 degrees of warming is like half the height of the country, the north-southness of the country. Not saying that we're going to have the climate of Texas, but 10 degrees of warming is like the difference between here and Texas. So I got one more bad thing to tell you about, which is that the CO2 is going to last for a long time. A lot of times when people talk about what to do about climate change, the fellow here asked me what I hope to hear in Obama's speech tonight. You think about changes in emissions, right? The emissions is like the faucet, but the CO2 in the atmosphere is like the bathtub. Turning down the faucet doesn't make the water go away. Turning down the faucet just means the water is rising less slowly. So getting rid of the CO2, which is emitting heat down on the surface of the earth, means you have to drain the tub, and that takes a very long time. Worse, we're not really in control of the faucet, let alone the drain on this tub. I had an opportunity to go to China last spring for CSU. That's too far for me to go for spring break, but I went for a recruiting trip for CSU. This is Shanghai, China. This is in 1990. This is a really cool place. We got to walk through here. This is called the Bund. It's a very old neighborhood in Shanghai, kind of colonial. You'd swear you were in Germany or France walking through there. Beautiful old sort of colonial looking architecture. There's a clock tower here, but instead of like bing dong ding dong, it does this Chinese tune, you know. I mean, I can't do those, but this is the same place in 2012. Okay, let me do that for you again. 1990, 2012. Same spot, okay? Shanghai is incredible. I couldn't believe it. I was delighted to get to visit. The population of the city proper of Shanghai is 22 million, and there's a whole mess of suburbs around Shanghai, each of which has more than 10 million people, and you've never heard of any of them, probably can't pronounce them. But it's amazing. It's like the capital of the world. Very wealthy, bullet trains and excellent subways and beautiful lavish hotels. I mean, I'm sure there's slums, but they weren't showing us those. But the point here is that, I don't know if you realize this, there's 300 million people in the United States. China and India together have 10 times that many people. 10 times as many people in China and India as are in the United States. There's 7 billion people on Earth today, but only 1 billion of us live like we do. And by the end of this century, if business as usual continues and Plan A comes to fruition, instead of 1 billion people living like this, 4 billion people will live like this. Let me put it a different way. The population of the world will only increase by something like 40% in this century, but the amount of CO2 emissions will probably increase by 400%. The rate of emissions growth is 10 times the rate of population growth because all those billions of people aren't going to stay poor. And that's a good thing, right? No wonder. They don't want to stay poor. They want to live it up. They want to live like us. Can't blame them. We've got to figure out a way, somebody's got to figure a way, you young people and your children are going to have to figure out a way so that all those billions of people can live decent lives without filling that bathtub and overtopping it and putting all this heat-emitting gas in the atmosphere that's going to change our places out from under us. So that's actually common myth number 2. If we reduce or stop burning fossil fuel, the CO2 will go away. Ain't going to happen in a long, long time. Eventually it will. But in the time scales that we're thinking about, not so much. This is not a prediction, okay? This is a what if. Here's the year 1800. I don't know, think back, Napoleon, Ben Franklin, Thomas Jefferson. Fossil fuel emissions, here we are today, roughly 10 billion tons a year of fossil fuel emissions. By the end of this century, roughly 30 billion tons a year of fossil fuel emissions. Let's just say, what if in the year 2100, people decide, oh my gosh, we got to do something about this, and they turn it off, all the way off, all the way off. The CO2 barely goes down at all by 2300, and the warming continues to go up. It takes a really, really long time to drain that tub. All right, so this is bad. We happen to live in a place that's extremely vulnerable to this stuff. Because we live in, so if you haven't figured it out, we're in the second S now. This is the serious part. We live in a place that doesn't have enough water. This is a map of annual average precipitation in Colorado. I don't know, we live there, Larimer County. This whole big orange area gets 10 to 15 inches of rain a year. But did you know that over 5 million people live in Colorado? Guess what? There's not enough water there is enough water, but there's only just barely enough water for 5 million people in Colorado. And if a lot of it started evaporating more than already evaporates, we'd be in a world of hurt. What would that do to the value of your house? What would it do to jobs in Colorado? What would it do to your retirement fund or your children's education? I mean, this is not about polar bears, this is about us. What would it do to the ski industry? I'm going to kind of skip through some of these because I bet you already knew these things. Warmer winters produce red forests, which catch fire. You probably kind of knew that, especially if you were around here last summer. Warming, we happen to be in a very, very vulnerable place. Obviously, if you were given a talk like this in Connecticut or New York, you wouldn't be talking about pine beetles, you'd be talking about sea level. But we're not worried about sea level. We're a mile above sea level. If the sea level ever gets up here, we've got other problems. So we know for sure that CO2 molecules absorb and emit heat. Okay, it's been known for 150 years. We know for sure these 4 things don't have error bars on them. We know these things absolutely certain that doubling the number of CO2 atoms, molecules, would add 4 watts to every square meter forever. We know for sure that if China and India grow their economies with coal, that we won't just have 1 doubling, we'll have 2 doublings. We'll go to 4 times pre-industrial CO2 in this century, and that's not 1 4-watt light bulb on every square meter, it's 2 4-watt light bulbs on every square meter because 2 doublings. Furthermore, I didn't really prove this to you, but we know that the extra CO2 will continue radiating heat down for thousands of years after we're done burning the coal. This is a problem. This is the serious part. We're not really all that sure about exactly when and exactly where and exactly how this climate change is going to happen. What's more, as a scientist, I don't know what that's going to do to the economy or to politics or to social systems. Furthermore, nobody really asked me, except as a voter, what to do about all this, right? It's not my job to tell you what to do. That's everybody's job. Everybody's job together. We're all in this together. We all get a voice in what to do. But the worst myth of all is that without the cheap fossil fuel, it's the end of civilization. You're going to freeze in the dark. You're going to starve. The sky is falling. Be skeptical about this one, okay? Personally, I don't believe it. I don't believe that there's no way out of this. I do believe that this can be solved. I think that a clear-eyed look at what our ancestors did to get us here shows how incredibly resilient people can be, how incredibly creative people can be. A famous quote of a climate scientist was like, look, our grandparents had the Nazis to deal with. At least all we have to deal with is climate change. That's kind of a different perspective on it. People people have been dealing with problems for a long time. When I was a little kid, the entire world economy used to put 2 billion tons of carbon a year into the atmosphere, and now it's 10. I mean, it says it's 8 on here, but that's because it's an older slide. There are some colleagues of mine at Princeton that this place called the Carbon Mitigation Initiative, you can look it up online, that gave me these slides. If you follow our current path for the next 50 years, we'll double emissions again to something like 16 billion tons of carbon per year. And they asked, what would it take instead to follow this flat path and just, now this isn't going to make the CO2 go away. This is just not opening the faucet any bigger, any stronger. You're not draining the tub, but you're leaving the faucet at the setting it is now and just filling the tub at the same rate that you were. And the difference between that current path and the flat path is a triangle, so they called it the stabilization triangle. They set an interim goal. They're not really recommending this. It's a what if. What if we set an interim goal that 50 years from now, the faucet would be right where it is today? And then they divided that interim goal into even slices, which they call wedges. So you can find this online, this whole thing, under climate wedges. Just Google climate wedges, it'll be the first hit. So each of these wedges is some way to offset 1 billion tons a year of emissions 50 years from now. And you get 50 years to do it. The nice thing is that they start with nothing and they grow. So you start with whatever we have today, and then you allow 50 years to figure out how to offset 1 billion tons of carbon a year in emissions. And they made this job more difficult because they said, we're only going to look at existing technology, no breakthroughs, no cold fusion, dilithium crystals, nothing like stuff that's only in the lab. In fact, they said we're only going to restrict our analysis to technologies that are not only existing today, but commercial today. Somebody's selling them and making money, and available at scale. Meaning it's not just some experimental technology, it's something you can actually buy in big wedge-sized pieces. And they, believe it or not, found 15. Remember, you have to find 8 to be able to hold the faucet at the same level for 50 years. Astonishingly, they list 15 different available commercial at-scale technologies that could together provide all of this energy so that all those billions of people on the other side of the world can start to live decent lives without putting CO2 in the air. It's a wonderful thing. And there are, renewables like you might expect. There's energy efficiency and conservation. There's different fuels, and there's nuclear power. Now, I'm warning you, you're not going to like all the wedges, okay? Different people like different wedges. That's fine. That's the way, politics works. Efficiency is everybody's fave because it's cheaper than free. Get this, in 50 years' time, if you make your wedges out of efficiency, you have more money in your pocket at the end of 50 years than you would if you didn't do these things. So these are the low-hanging fruit, the no-brainer solutions. Just to give you a sense of how big a wedge is, everybody wants to change our light bulbs, right? You put in the compact fluorescent light bulbs. If every light bulb in the world were to change to a CF or LED light bulb, that would be 1/4 of one wedge. Okay, so that's nowhere near enough. You got to have 8 wedges just to hold the emissions flat. If every car in the world got twice the gas mileage that it gets, that would be 1 wedge. Now actually that's easy, believe it or not. 50 years is like forever for cars, right? All we're talking about is getting the equivalent of everybody having a Prius 50 years from now. No problem. There's other wedges that can be gotten in here. Probably the easiest stuff is buildings, better insulation, better roofs, better HVAC systems. All that kind of stuff actually pays off in spades in 50 years. You wind up having more money at the end of 50 years if you build better buildings than if you build crappy buildings. So you can easily get get 3 wedges, maybe 4 out of efficiency, and have money left over at the end to pay for other stuff. This one is controversial, fuel switching. Now, this is weird, but it turns out that liquid fuels have twice as much energy in them per unit carbon as solid fuels. So if you burn coal to make electricity, and you burn gas to make the same amount of electricity, twice as much CO2 comes out of the coal. The coal has more carbon-to-carbon bonds, and the gas has more hydrogen and carbon bonds, and it produces more energy for less carbon. It turns out that if you built 1,400 big electrical plants over the next 50 years with gas instead of coal, that's a wedge. And it's easy. The gas is abundant, the technology exists. Even now, gas is displacing coal, and emissions are going down because of the replacement of coal with gas. In China, they're building 2 giant coal-fired power plants a week to support, development of their economy. If they used gas instead of coal, that would produce a whole lot less CO2. Probably the most expensive wedge there is called clean coal technology. You've heard about it. You dig the coal out of the ground, you bring it up to the surface, use it to make electricity, use about 1/3 of the electricity to capture the coal at the smokestack, and you compress it into a liquid and you pump it back down where the sun don't shine. And so you get all the electricity out of the coal, but you don't put any CO2 in the air. It's definitely doable. It's incredibly expensive. And it takes 3,500 of these plants operating at full scale to make one wedge. The coal companies love this because they get paid twice. They get paid once to dig it up and once to put it back. So look for this in your neighborhood, whether you like it or not. But it's out there. Wind. We love wind. Wind is great around here. We've got lots of wind in Wyoming. We've got a big plant in Windsor that makes the turbines. The trouble with this is you need a lot of wind to get a wedge. You need about 1 million of those giant windmills that you've seen the blades going down I-25. Takes 2 semis to carry 1 blade. 1 million of those giant windmills makes a wedge. Okay, as long as you're willing to pay for lots and lots of windmills, we can get wedges this way, and we can probably get several. We have plenty of wind capacity in the air to generate a lot of electricity this way. It just takes money. It's not as much money as carbon capture and sequestration, the clean coal technology, but it's expensive. Solar is another wonderful, abundant resource. We have lots of sunshine in this part of the world. I have a neighbor that put these things on his roof. As soon as he put them on his roof, I'm like, oh my gosh, I got to have one of those. And I started looking online, and they're very expensive, but financing is available. Maybe this is going to be. The trouble here is getting a wedge. You have to make 700 times as much solar power as we have today to get one wedge, as opposed to 30 times as much wind. So there's trade-offs. You don't like all these things, that's okay. However you do it, you got to provide a decent standard of living for billions of people on the planet Earth, right? They're already here. It's not like it's future population growth you got to worry about here. These people already exist. They're just poor. And they don't want to stay poor, and you can't blame them. So billions of people, decent standard of living, lots more energy than we have today because there's all those extra people. And you got to do it without putting CO2 in the air. It's starting to sound hard, but it's definitely doable. I just listed however many wedges, however many ways to do this. These technologies are already in hand, they're already available, they're already at least marginally affordable. There are some trade-offs there. The trouble is it's politically difficult, and you're not going to get it by tinkering around the edges. This isn't going to be solved by riding the bus. It's like a wholesale replacement of the energy and economic system that we have with a new one that provides all this extra energy without putting CO2 in the air. Sounds hard, but you know what? Our ancestors did it before. I want to do a thought experiment with you. I want you to imagine the world of 1800. Napoleon was storming across Europe. Thomas Jefferson was doing the Louisiana Purchase. Ben Franklin, I guess, had graduated from playing with keys and was Secretary of State or something. But you know the story of Ben Franklin with the keys and the kites, right? Electricity. So imagine in that world, if somebody had come up, I don't know, obviously they didn't have the internet and they didn't have TV, but if somebody had come up with an idea and started promoting the idea that they were going to transform the world economy. And they were going to dig 8 billion tons of carbon out of the ground every year and build pipelines and super tankers and railroads and highways and trucks and deliver it to every 7-Eleven street corner on the planet. And cars, you know, they're going to take rubber tires and stick them on carriages and put internal combustion engines in them and drive them like hell. And there's going to be roads and bridges and off-ramps and on-ramps and all kinds of fun stuff, places to drive them. And electricity, that thing that Ben Franklin does with the kites, we're going to put giant power plants at Rawhide and run copper wires to every single house in every neighborhood on the planet. I mean, my God, somebody's going to come up and say, wait a second, you can't afford it. And they would have been right. Because if you add up the money, if you add up the cost of this system of wires and engines and roads and buildings and stuff that we've got now, and you put it in $1,800, forget about it. There wasn't enough money in the whole world to buy that in 1800. But they did. And they didn't go broke doing it, they got rich doing it. Not everybody got rich, but on the whole, the standard of living is higher, the amount of wealth in the world is greater today, having bought all that stuff, than it was before they bought all that stuff. That's the way economy works. I mean, I'm a scientist. It doesn't work like this for us, right? We got like conservation of energy and conservation of mass and all that stuff. Economics is like magic. When somebody buys something from somebody for $1 and they both agree that they got a good deal, there's more than $1 of value. That's like fundamental to free market economics. People have to build the future and sell the future to each other, and there it is. And all we have to do is what our ancestors do. We had to not be wimps about this. I have colleagues here at CSU, lots of them, and it's not just CSU, who basically will tell you that the wealth of the world is extracted, okay? That there's value in a lump of coal. And that value gets multiplied when that energy is sold around and around and around until there's lots of money available around. That the basic underlying wealth in the world came out of the ground. I hope they're wrong. I don't really know. I'm not an economist. Economists don't know either. But if they're right, the whole thing is a house of cards. Because as soon as you run out of the stuff to dig up, the whole thing collapses. Let's hope they're wrong. I have a different vision. I believe that our well-being depends on creativity, on hard work, on ingenuity. That our most precious resource is us, not something we dig out of the ground. And that before we run out of the stuff to dig out of the ground, we'll create, we'll invent, we'll produce the world of tomorrow. And as long as our kids are as smart as our parents, and our grandchildren are as hardworking as our grandparents, the world is going to be okay in the end. Thank you for your time. Yes?
Among college students, how many of them agree with you?
I get applause pretty much every time I give this slide, so I'm hoping that means they agree. I don't know.
Do you think it's 50% or do you think it's higher?
Who buy this last line?
We took
No, I don't know.
all college students.
How about, what do you folks think? Do you think the world's going to fall apart when we run out of coal, or do you think smart people are the precious resource?
I think that we're a lot like, not to put old people down, we are starting to understand what it's going to take, and we're a little bit more okay with taking on that responsibility. So I don't know if it's like part of like buying into it. I don't know if it's like this con necessarily, but it is going to be something we have to work hard toward.
You know, I think that history shows that people deal with these problems, that you know, stuff, the plague, you know, the asteroid that killed off the dinosaurs. Well, that was too bad for the dinosaurs, but it was great for us, right? We wound up winning from that one. I don't know. People are more resilient than that top bullet gives them credit for, in my opinion. So it's simple. Heat warms things up. It's serious. It's going to bite you in the butt. You're going to have to figure out how to deal with it. So you will. That's the solvable. Yes?
You talked about the difference between turning off the faucet and stopping the bathtub. And you talked about these wedges as turning off the faucet. There seems to be a disconnect there. Is it a solution or is it a lessening of the concern?
Well, eventually the faucet has to go all the way off. Okay? This is not something I emphasized in the presentation, but in order for billions and billions of people to live decent lives and have plenty of energy, in my opinion, there's no way around it. That we have to do that without any emissions. It's not, a cut in emissions is not going to solve that. But of course, to get to zero emissions, you have to start turning down the faucet. You can't get to zero without going through all the other numbers in between.
Is anyone looking for solutions to take out the plug and get some of the CO2 out of the atmosphere?
Well, sure, but it's very hard. It's much, much easier to not put it there in the first place. So the trouble is that, think about this. Again, this is like grade school stuff. There's energy in the bonds of coal oil, and natural gas. And we break those bonds on purpose because it's fun, right? Because we get energy out. To take the CO2 that's already got the bonds broken and put it back, we have to put energy in. So pulling CO2 out of the atmosphere will require energy. Where are you going to get the energy? Burning a lot of coal? No, that's not going to happen. So, maybe with like giant nuclear power plants, you could create enough energy to suck CO2 out of the air, but wouldn't you really rather run your economy without putting CO2 in the air in the first place so that you didn't have to take it back out? Yes?
So a big claim by a lot of people who are naysayers of climate change is that several natural events in a hurry will equal all the crap that we do, such as Pinatubo.
No, well, okay, that's a quantitative statement, and that's just flat out not true.
That's what I'd like to discuss.
Okay, so from a CO2 point of view, we know how much carbon there is in the air. You can measure it. It's really easy to measure. We know how much fossil fuel we burn. And the reason why we know that is because we make trillions of dollars buying and selling this stuff. And so stockholders have to know how much stuff they sold. And you do the math. We put X amount of carbon into the air every year, but only half of X actually stays in the air. The other half is absorbed in the oceans and the plants. Pinatubo, or any volcano, doesn't even make a visible blip on that graph. It's like 1,000 times less than the amount of CO2 we put in the atmosphere every year. So, 1,000 Pinatubos in a year would be a big problem, but it wouldn't be a CO2 problem. It would be a volcano problem.
It's very simplified what you seem to be saying, and I'm wondering if you're missing thresholds in some of these feedback mechanism effects.
Yeah.
Because some people have looked at like 16 thresholds to global system balances and things. So when you increase the acidity of the ocean, you do these other things when you go above 4 degrees, and
Yep.
things like that. You could have catastrophic
You could.
effects before and you're saying that our future is bright, that somehow we're going to, cut it off before some of these effects. Or we're going to wait till it happens, and somehow we can go back. A lot of these, once you cross a threshold, you can't.
You have an excellent point. So there are thresholds in the climate system, and it is quite for one of the most one of the most obvious ones is this: if the temperature gets high enough to melt the ice in Greenland or Antarctica, all the coastal cities of the world will be destroyed, and that's pretty serious, right? 40% of the world's population lives close enough to the sea that they'd be underwater if you lost the ice. Other things like the permafrost melting and releasing all the methane. There are very serious problems out there. I guess for my own sense, I prefer to encourage people to solve this problem rather than say, oh my God, it's the end. You know, I
think you need to make it though that how serious.
I really think it's deadly serious. And I think it's so serious. It's so serious and it's so boneheaded obvious that heat warms things up that very soon, I mean, hopefully by the time I'm dead, everybody else will think this is obvious too, and we will turn off that tap. And the sooner we turn it off, the less chance we have of destroying every coastal city in the world, melting the permafrost, you know, crashing the climate system. I agree that it's a very, very serious problem. I don't mean to belittle the problem. But I also have a lot of faith in people. Ah, you're shaking your head. Maybe that's the problem, is that I have a lot of faith in people. I have children. I have a 19-year-old and a 15-year-old. And I want to believe that they and their generation will make it right.
It's just that your wedges, you know, a lot of them take political will. And if we look at the climate conferences from the last 30 years, the U.S. is one of the reasons that these things don't happen, and China and other large countries.
I agree.
There was a sociologist here in April from Oklahoma State University talking about a number of things that you discussed, but he also talked about where the U.S. is compared to where other first world nations are. Give you a little he talked about us being in terms of acceptance of the same level as some African countries. And if you talk to people like from Australia or somewhere, they're not talking about whether or not it's real. They're talking about arguing about how to solve it. So
Yeah.
it's
So
not a worldwide denial.
I was at a meeting last week in Albuquerque, and we had a speaker, Bob Inglis, who's a former Republican congressman from South Carolina, from one of the reddest districts in one of the reddest states in the United States. And he lost his seat in a primary challenge, largely over a question about global warming. He was asked about global warming and whether he believed it was a problem. He said it was, and he lost his primary. He wasn't able to run for election. He's now working at George Mason University, and he does a lot of presentations about climate change. He's a very, very conservative politician. He favors this is not my point of view. This is a extremely staunch conservative Republican's point of view. Forgetting about cap and trade, and instead replacing some taxes with taxes on fuel. So, for example, he said, suppose we replace the payroll tax that supports Social Security with a straight-up tax on coal. Suppose that we, dollar for dollar, no extra revenue for the government, but a very, very steep tax on coal. Suppose that we replace the corporate income tax with a tax on oil and allow the market to feel this extreme cost of burning fuel. Watch them invent non-carbon ways to make money. And this is a very staunch Republican talking. I find that stuff pretty compelling. I think if this country decided to take this as seriously as the Nazis, we would solve it. I do. I may be wrong. I'll buy that. But I hope not.
One other point, isn't it true that when, now back to the volcano question, you're also dumping a lot of particulates up there?
That actually cools the climate.
So some of the
Aerosol in the stratosphere, yep.
so they're offsetting themselves a little bit.
Yeah, but our problem is not a volcano problem. Our problem is a CO2 problem. In a quantitative way, there's just no, they don't even you couldn't put them on the same graph.
That's the point I think.
Yeah, I got another one like that. Just I know you got a question. So 4 watts per square meter, right? What does that mean? It means one light bulb on every square meter of the planet. You've heard of the Little Ice Age? Maybe not, or the medieval warm period. These times 1,000 years ago when climate was different. That was 0.2 of a watt. Okay, this is 20 times that much. Holy mackerel. The big ice age was only 7 watts per square meter difference. And we're talking about 8 watts per square meter in this century because of China and India. Holy mackerel. We're talking about as much climate forcing in the 21st century as the difference between the ice age and now. Wow. Yes.
So you mentioned China a little bit, its challenges that it's facing and trying to bring 300 million people into cities in 25 years. That government, Communist Party, is run by engineers and technocrats that are taking this very seriously and are trying really hard to do it in a way that's going to keep them going forward. Do you think they're doing enough? Do you think that they're trying? I mean, they're investing millions in solar.
Their fossil fuel emissions are now higher than ours. So, eventually that's going to have to stop. Stop to zero. I mean, eventually, to really solve this problem, you got to turn that tap all the way off and let the drain work.
And they have a lot more ability to control what their markets and economy does.
That's true.
And so, I mean, they have the ability to do it. Why aren't they?
They really don't. All those plants you're talking about, 2/3 of them are illegal.
Or what?
In China, all those coal plants that they're opening, a huge number of them are illegal in China.
Illegal.
Yeah, they're outlawed by their own government.
Well,
But they don't have a real good handle on that, obviously.
this is a hard problem. But, I mean, as I said, if you put the past in perspective, what our ancestors did was at least this hard, right? They replaced horses and buggies with jet planes. How the hell did they do that? It's too expensive. Baloney. Sorry. Yeah, so, nope. Maybe we're done. Oh, one more.
So what about the small things that individuals can do? Like the wedges at scale?
They're big.
It's the only, in one sense, it's the only solution. But what about you and me and each of us? Does it matter or does it not matter?
I think it matters to a lot of us. I was going to say psychologically, I might almost say spiritually. It matters to us inside in terms of what we choose and how we live and how we teach our kids and how we conduct ourselves. If you want to turn off that tap at the same time that you bring billions and billions of desperately poor people out of poverty, I honestly don't think you're going to do that by riding the bus. But I think you should ride the bus. Okay. Are we done? No, one more?
I think the reason that our individual actions are important is because it's impossible to speak with authority.
If you're
You don't. I mean, part of the reason that Al Gore was not successful is because he was living in a way that said he didn't believe it. Even though intellectually he believed it, but it didn't.
okay, well, I'll buy that.
And so people
So
say he doesn't believe it.
I have to say this is getting pretty far from my expertise, but like you, I feel like I ought to do my part. But I still don't think that's enough. I think we have to go beyond that. Should we wrap it up? Thank you.